Dear friends, welcome to the 11th lecture on the course Risk and Reliability. This lecture is the 11th lecture in module 2, where we are discussing about the reliability theories and structural reliability. So, this is going to be lecture 11, where we will continue with the system reliability as a continuation of the last lecture. So, I call this system reliability 3. In the last lecture, if you remember and recollect, we discussed about general systems, and we said it is actually a combination of system in series and system in parallel. Series systems are those systems where if any one component fails, system failure is certain. Parallel systems are those systems where if all components fail, then the system is failed. So, for a given general system, we identify the cut sets and the path sets. From the cut sets and the path sets, we then derived minimum cut set and minimum path set. So, now based on that system, we are going to discuss the failure theory, but let us recollect a new general system now, which is going to either comprise of minimum cut sets or minimum path sets. So, let us reproduce the same example again for our understanding, and let us draw a general system with minimum cut set and minimum path set. So, if you look back, this was the general system we had. We said this is 1 and this is 2, this was 3 and this was 4. This was the general system, which is of course the combination of series and combination of parallel systems, as you see from here. For this, of course, it is expandable in either way. For this, we identified the minimum cut sets, which are C4, which comprises 2, 3 and 4, which comprises 1 and 4. Similarly, we also had minimum path sets, which were P1, P2 and P3. P1 is only 4 and P2 is 1 and 2 and P3 is 1 and 3. Okay. Now, we are going to form a system which is comprising of either minimum cut sets or minimum path sets. So, now we are going to form a general system assumed to have a combination of either a series system with its minimum cut sets or a parallel system with its minimum path sets. Okay. Let us represent this graphically. General system with cut sets which is going to look like this. The cut sets are 2, 3 and 4. The other cut set is 1 and 4. Of course, they need to be connected because I want them to remain in series, that is what I am looking at, because a general system with minimum cut sets will behave as a series system. So, I put them in series, the system is now subjected to the load. So, this was my C4, this was my C1, this is now general system which comprises the minimum cut sets, and this system is now going to behave as a series system. Please understand, system which is in series is said to be failed if any one component of the system fails. Okay? Similarly, let us say a general system with minimum path sets. The path sets are 4. So, let us connect them. 4. Then it has got 1 and 2. It has got 1 and 3. Okay. So, this was my P1, this was my P2, this was my P3. When I reproduce a general system with minimum path sets, the system will behave as if it is a parallel system. So, now they are behaving as a parallel system. When I reproduce a general system with minimum cut sets, the system will behave as a series system. Now, they are in series. Okay. These are two cases now. I have now modified the general system, which is a combination of series and parallel, by identifying the minimum cut sets and minimum path sets. I have reconstituted the general system either with minimum cut sets or with minimum path sets. So, one will behave as if it is a series system, one will behave as it is a parallel system. So, now the complexity of identifying the failure of a system either with all components failing, which is a parallel system, or any one of the component failing, which is a series system, is now simplified to either a series or a parallel, for which independently one can easily identify the failure systems. Okay. The complexity in a general system is now simplified to a series or a parallel system. Of course, understand the system now comprises of components of minimum cut sets or minimum path sets. Therefore, it is very important for a given system to identify the minimum cut sets and minimum path sets. So, now interestingly, I call this as figure number, let us say 1 for our understanding, and 2, this is series system, this is parallel system. So, as shown in the figures here, each minimum cut set is actually a subsystem of parallel components, correct? Is actually a subsystem of parallel components, is it not? And each minimum path sets is actually a subsystem of components in series. You can see here components in series, but it is a parallel system. Now, for a cut set formation which can be seen in figure 1, for a cut set formation the system will fail if components 2, 3 and 4 fails, because it is a parallel system. Okay. Is it clear? Simultaneously. Okay. And or components 1 and 4 fail simultaneously, because 1 and 4 are parallel, 2, 3 and 4 are again parallel. If you carefully look at this figure and this combination, you can always say no other possible combination of component failure exists, is it not? So, I can say no other possible combination of the components failure, is it not? Can constitute failure of the system, correct? Now, for a path set combination, which you can see from figure 2, as you see here, it is very easy to verify that the system survives if any one of the series subsystem survives, is it not? Because they are in parallel. Okay. So, the system survives if any one of the series subsystems survives. Okay. Having said this, let us say having said this, function for the general system, that is the failure function, performance function of the general system is given by A z, which is pi function of m minus 1 to n c of A, where I call equation number 1, where n c is the number of cut sets, A is the cut set function, of the mth cut set. Now, you can see here this system actually, this equation is of the similar form of that of a series system, is it not? So, pi function. for which the cut set function is given by alpha m a. Interestingly, the cut set function is again in parallel, is it not? Therefore, that is going to be 1 minus pi of, that is the parallel system function, I is equal to C m 1 minus a equation. So, alpha m a which is used here is given by, because now in this system each one of them remains as parallel, is it not? Therefore, the function failure is going to happen from this equation. In this case, C represents the mth cut set. Cm actually represents the mth cut set. Therefore, for the general system, system function is now given by Az, which is 1 minus A2, 1 minus A3, 1 minus A4. These are the combinations we have of that of 1 minus A1, 1 minus A4, I will call this equation number 3. Now, for the Boolean variables, you have a special property. These are Boolean variables. Why? Because they take only values of 0 and 1, failure or success. For the Boolean variables, we know that Aik is equal to simply Ai of k or Ai if k is greater than 0. Applying this, the above condition, we get Az as A4 plus A1 A2 plus A1 A3 minus A1 A2 A3 minus A1 A2 A4 minus A1 A2 A3 plus A1 2 3 4. Equation number 5. Same argument now we can apply for the general system with minimum path sets. So, for general system, with minimum path sets, system function can be given by is 1 minus I is equal to 1 to n p one minus beta I of equation number 6. This is n p, where n p is the number of path sets and beta I of A is the path set function for the ith path set. The path set function is given by beta I of A is pi I element of pi of A, because in parallel system and path sets all will remain in series. Okay? So, we use that equation, equation number 7, where in this case pi is the ith path set. Therefore, for general system, function will be given by Az 1 minus A4 1 minus, that is what we are looking at. You look at this figure, A4 1 2 1 3, okay. 1 minus A1 A2 1 minus A1 A3. So, expanding equation 8, we get Az is equal to A4 plus A1 A2 A1 A3 minus A1 A2 A3 minus again A1 A2 A3 minus A1 A2 A4 minus A1 A3 A4 plus A1 A2 A3 A4. You will obviously see this is as same as you got it for the function expanding with the series systems. So, one can follow either way of finding out the failure of the system reliability for the general systems, either comprising of minimum path sets or comprising of minimum cut sets. You will end up in the same function of failure. Okay? Now, actually I am interested in computing the system reliability now. Now, for Aij, where j equals 1 to n for the components, and Az for the system, which contains Bernoulli variables let Pi be equal to P of Aj set to 0, which denotes the probability failure of the ith component and let Pf equals P of Az to 0 denotes probability of failure of the system. So, Z denotes system and J denotes the component. I mean, in fact, it is Aj. Okay. Having said this, for the ith component, we can write expected value of Ai 1 minus Pi and 0 Pi, which amounts to 1 minus Pi. Equation 10. Hence, Pi is expected value in this case of A bar j, where equation number 11, A bar I is 1 minus Ai, okay, this is going to be I, right, because we are looking at Pi. 1 minus Ai is actually the complementary even Ti, is it not? It is 1 minus Ai. Similarly, Pf, probability of failure of the system, is expected value of A bar z, which can be 1 minus E of Az, which can be 1 minus E of function of A, where A bar z is 1 minus Az. In terms of component level reliability analysis, one can say that event Ai set to 0 is equivalent to, that is what you see here, is it not? Ai set to 0, Ai set to 0 is equivalent to some function which is Gi of x is less than or equal to 0, which is a failure function. In other words, the ith component, that is ith component fails when the outcome of the random variable in a given problem defines a point of value domain. Okay, that is what it means. So, the ith component fails when the outcome of the whole random variable is lying in the failure domain. Now, for a system in series, which is consisting of n components, system fails if any one of these component fails, we know that. Therefore, the failure domain of a series system is nothing but the union of component failure domains which can be given by, let us say, the expression which is union of I equals 1 T n, that is the number of components, g of x failure domain. So, less than or equal to 0, equation number 40. For a parallel system, which is consisting of n components, system fails if all components fail. Is it not? Therefore, failure domain of the system, or let us say, to be very particular, of the parallel system, which I am going to say as sigma p, is the intersection of the component failure domains, is it not? Which is given by n number of components equation number 50. So, we will try to plot these failure domains and try to understand the limit state function surfaces, which indicates the region which is safe and which is corresponding to the failure. So, friends, in this lecture we extended the discussion of general system as a combination of series and parallel systems. We replaced a general system with minimum cut sets or with minimum path sets. One system becomes either cut sets in series or path sets in parallel, and the subsets in each one of them is vice versa. The subsets in a series system are parallel, the subsets in a parallel system are in series. So, one now understands the failure of either a series system or a parallel system, which is going to amount to the failure of the general system. So, we did derivation for both independently and showed that both of them exactly gives you the same limit state function Az, where Z is the system variable and I is the component variable. Then we further extended the discussion to understand the failure function or the failure domain of the series systems and the failure domain of the parallel systems. Once we understand this, try to plot them graphically and show the failure surfaces for both of them independently and see how we understand really the system failure in detail, which we will see in the successive lectures. Thank you very much and bye.